Okay, so welcome to this video looking at the physics of pirate treasure. So in this video, we're going to look through a scenario based on pirates dropping their treasure in the ocean and look at some of the physics involved. So we're going to be looking at some mechanics, some thermal physics, and even some of the Doppler effect later on. So we're going to start by just checking a few definitions. So you can get a copy of this task booklet from the link in the description. So get hold of it and have a go at defining each of these key things, and then we'll take a look. Okay, so first off, let's work our way through. So Archimedes Principle states that the upthrust from a fluid is equal to the weight of fluid displaced, or sometimes you see buoyancy force in there instead of upthrust. Density is the mass per unit volume. Pressure is the force per unit area. So moving through the remainder of the definitions, Newton's second law states that the resultant force acting on an object is equal to its rate of change of momentum. The first law of thermodynamics says that the change in internal energy of an object is equal to the work done on it and the thermal energy transferred to it. Specific heat capacity is the thermal energy transferred to change the temperature of 1 kilogram of substance by 1 degree Kelvin. Conservation of energy states that energy cannot be created or destroyed, only transferred. And conservation of mechanical energy states that the total mechanical energy of a system remains constant as long as no external force acts on it. Okay, so those are our definitions. We're now going to move on to some of the scenario parts of this. So again, pause it and have a go at some of these questions and then review them as you go along. Again, there's a link in the description to the task booklet. So we've got a treasure chest. Obviously, there's pirates. They're looking after a treasure chest. And we're going to model it as being a 50 centimeter by 50 centimeter by 50 centimeter cube. And it falls from the ship to the bottom of the ocean. So first task is use Archimedes Principle to explain why it is impossible for a box full of gold to float. Well, first we're going to generate an expression for the weight force of the box, which would be mg. But instead of the mass, we're going to put the density of gold times the volume of the box. Then we're going to generate an expression for the weight of water the box would displace. So it's going to be very similar, except it's going to have the density of water instead of density of gold. And that's the key. So because the density of gold is much greater than water, the weight force of the box is always going to be greater than the upthrust from the fluid. Therefore, the resultant force is always downwards to make the box sink, even if the box is fully submerged. So gold has a density of 19.320 tons per meter cubed. Calculate the mass of the treasure chest if it's 80% gold, and we can ignore the mass of the wood or the air in the box. Okay, so first of all, to get mass, we're going to do density times volume. It's 80% gold, so essentially 80% by volume, so that's why there's a 0.8. We've times by 10 to the 3 to convert it into kilograms per meter cubed. And all of the lengths have been converted into meters before cubing them, giving us a total mass of 1932 kilograms, or just under 2 tons, which is obviously very heavy, but it's full of gold, so it's going to be pretty heavy. Okay, so in mechanics, we often ignore air resistance when an object is traveling at low speed. Suggest reasons that would be inappropriate to do this with a treasure chest falling through water. So the key here is to understand what a drag force really is. So the particles of water are going to be much closer together than the particles of air because it's a liquid rather than a gas. So the same surface area of the chest will collide with many, many more water particles, and that's going to give a much higher drag force that you cannot neglect even at low speeds. So next question, would the drag force be higher at terminal velocity in water or at terminal velocity in air? Explaining your reasoning. So this is one you have to be very careful. The drag force would be exactly the same because at terminal velocity, drag is equal to the weight force. So that would be the general answer that would be appropriate here. However, legendary answer to this question the buoyancy force from water would actually exert a greater upthrust than the buoyancy force from air, that would mean the drag force could be smaller for the resultant force to be 0. So you could actually have answered water if you link it to buoyancy, but as a general rule, roughly the drag force would be equal to the weight force. Would the treasure chest's terminal velocity be higher in air or in water? Explain your reasoning. So it's going to be higher in air, and it's the same reason as we had before. The spacing between air molecules is bigger, so the object would have to be traveling much faster to collide with the same number of air molecules as it collides with at a lower speed in water. So essentially, because of a much lower density or much bigger spacing between molecules, you're going to have to collide with many more of them, which means you're traveling faster. When it lands on the bottom of the ocean, would the box be more likely to break when it lands and comes to a stop during the collision, or it bounces off the bottom? Explain your answer, assuming collision time is approximately the same in both cases. So the correct answer is bouncing. It will be more likely to break if it bounces. So if the collision time is the same, Newton's second law states that the object experiencing a greater momentum change will be the one that experiences the biggest force, and the one that changes direction will experience the biggest momentum change. Okay, so when it fell, the box contained 4.2 decimeters cubed, or 4.2 liters, of air at atmospheric pressure of 1.01 times 10 to the 5 pascals. It was initially at 20 degrees Celsius. Calculate the number of moles of gas. So what I'm going to do here is use the ideal gas equation. We want the number of moles, so we want to make N the subject. First thing we need to do is convert liters into meters cubed. Now the conversion I use is I know 1 decimeter cubed is 1,000th of a liter. So that's the conversion there. But you should know that deci as a prefix means 10 to the minus 1. So when you cube it, it ends up being 10 to the minus 3. And the other thing you have to remember here is to convert into Kelvin, so 20 degrees plus 273. And when you do all those things, you get the number of moles as 0.17 moles. So explain why, as it falls to the bottom, the box is likely to implode, which is the opposite of explode, so essentially burst inwards on itself. So the pressure on the outside of the box is going to be increasing as there's a greater weight of water acting on it. So as the box falls in the ocean, the weight of water above the box increases, which means there's going to be a higher pressure on the outside of the box. And the other thing is the pressure on the inside of the box would be decreasing as the temperature of the gases decrease as it transfers internal energy to water. So the oceans are much colder than the air above them, so the temperature is going to be decreasing as well. So both of those two things act to increase the pressure difference, and that could create a resultant force to compress the box inwards, which will cause it to implode. However, as it reaches the seabed, the box falls into a vent which pumps very hot water into the ocean. If the top of the box is 2,500 meters under the surface of the ocean, calculate the temperature of the gas in order for the gas pressure to equalize the water pressure on the top surface of the box. Assume no gas is able to leak and the water is uniform density of 1,000 kilograms per meter cubed. Okay, so the first thing we can do is calculate the pressure on the top of the box, and this expression here would calculate that. So based on the height of the water column above the box times by the density and times by G gives us a pressure of 2.45 times 10 to the 7 on the outside of the box. So because no gas is able to leak, the number of moles is the same, and the shape of the container is going to stay fixed, so V is constant. So what we can use is P over T is equal to a constant. We know the initial pressure, we know the final pressure, we know the original temperature in Kelvin, therefore we can calculate the final temperature in Kelvin there. So you can see that to make the pressures equalize, it would have to be incredibly hot in order to be able to accomplish that. So calculate the thermal energy transferred to the box, assuming the box volume remains constant. The specific heat capacity of gold is 129 joules per kilogram per Kelvin. You can assume that the box is only gold and air, but you cannot neglect the energy transferred to air. So the first part is fairly straightforward, using Q equals mc delta T to figure out the thermal energy transferred to the gold. The more challenging part is figuring out the thermal energy transferred to the gas, as we haven't been given its specific heat capacity. However, using the first law of thermodynamics, if the volume of the box is constant, there's no work done on it. So the thermal energy supplied will be equal to the change in its internal energy, which will be equal to 3/2 nR times the change in temperature. So we know the number of moles, we know the molar gas constant, we know the temperature before and after, so we can calculate the thermal energy we'd have to supply, which you'll notice is considerably less than the thermal energy transferred to gold. So then, once we work out the total thermal energy, it's pretty much the thermal energy transferred to gold. The others more insignificant. So that kind of links into the next question. So we calculated the thermal energy transferred to the gas. Was that necessary? Well, no. The thermal energy required to heat the gold was 10 to the 5 times bigger than the thermal energy transferred to the gas, so we could easily have neglected that if we wanted to, but the question was set up as a nice way of showing using the first law of thermodynamics. State an assumption you made about the gold for your calculation in part X. So the assumption we made is its melting point is above 71,000 Kelvin, so that we didn't have to consider its state changing as part of the calculation. However, that's not likely to be valid, as the melting point of gold is 1,337 Kelvin, which I just looked up online. So you can see that that assumption was made, but is not really valid. Okay, so to measure the speed of the box as it falls, the ship's captain uses sonar, which is basically sound waves, and they're reflecting them off the object underwater to be able to locate them. That's how sonar works. Explain what the captain will notice about the sound waves reflected off the treasure chest. So this is a sneaky question about the Doppler effect. So the frequency will be lower than the frequency of the emitted waves, and that's because the object is moving away from the observer. Therefore, the Doppler effect will cause the wavelength to increase or the frequency to decrease. We wouldn't really say it has a lower pitch, although that would be true because the ship's captain is not really listening to it. He's using a device to send and receive the signals, much like ultrasound works. So at a specific moment in time, the box has a velocity of 12 meters per second. The speed of sound in water is 1,500 meters per second. If the initial signal had a frequency of 5,000 hertz, determine the frequency of the signal that is detected. And we can assume that the box is traveling parallel to the sound waves, or there's an angle of 0 between them. So if there's an angle of 0, we can get rid of the cosine term from this expression. They're reflected waves, so we have a 2 times the speed on the top, just like we do with ultrasound. And what we can do is we want to calculate the new frequency, so it's going to be the original one minus the change. So that's what I've done there. Plug the numbers in and you end up with a new frequency of 4,920 hertz. So if the box are traveling at an angle to the sound waves, explain the impact of that on the frequency of the reflected signal. So this is the full expression for reflected Doppler effect. And if you increase the angle, that's going to decrease the cosine theta term. So if the box is traveling at an angle, the frequency change would be smaller, so the reflected frequency would be higher than it was before. Okay, so explain why sonar devices are dropped into the water rather than sending signals from air into the water. And again, this is the same theory as goes alongside ultrasound scanners. So the acoustic impedances of air and water are very, very different because their densities are very different and their speed of sound in them is very different too. So what would happen is if you had it in the air, they'd all just get reflected off the water, and that would be fairly pointless trying to use it to detect anything. So if you put it into the water, you can avoid that problem. So the pirates locate their treasure, and to raise it to the surface, they attach inflated animal bladders to the chest until the buoyancy force is sufficient to lift the box to the surface. Explain why the box bladder system floating to the surface doesn't violate conservation of energy, seeing as both its GPE and kinetic energy are rising. So small side note here, this is one of the theories as to how they built the pyramids of Egypt by attaching animal bladders to float the blocks. So by attaching bladders full of air, your objective is to decrease the density of the overall object below that of water, so that then there's a resultant force upwards. That's the goal. So in terms of why that doesn't violate conservation of energy, well, essentially what's happening is work is being done on the system by the buoyancy force from the water. So the water outside is not part of the system, so the force from the water is an external force causing total mechanical energy to increase. So in terms of how that doesn't violate conservation of energy, if the water is doing work on the system, that means the energy of the water must be decreasing. And it is because what's happening is the water loses GP as it moves downwards into the space previously occupied by the object. So as the object moves up, water flows in to fill its space, losing GPE, so the total energy stays the same. Final question. We've got the chest to the surface. Now we want to lift it back onto the boat. And they have a crane based on a lever, like you can see in the diagram. So the total crane length is 5 meters, that's of the beam. Determine the working arm length, the distance from the pivot to the load, if the crew can provide a total force of 4,000 newtons. So what I'm going to do is I'm going to take moments about the pivot, so I don't have to consider the reaction force from there. And I'm going to call the length of the working arm x. So if it's going to be in equilibrium, what we're going to need to do is make the moment of the crew, which would be 5 minus x times 4,000, equal to the total weight force times by x for the load. And once we do that, we can rearrange and calculate the distance x, which is what we've done here. So to be able to lift the load, the x is going to have to be greater than that value. Okay, so that completes this case study on pirates losing their treasure. I hope you found that useful. If you have any questions, please feel free to comment and ask me, and I'll see if I can get back to you very soon.